Good afternoon, everyone. I'm going to be talking about CFD. We've heard the word a lot, and I'm going to give maybe a little different perspective on it as more of a practitioner, but I hope to inspire some of you and also maybe shed a little bit of light on things just from an engineering standpoint. Kind of as an outline, I want to first give my background in CFD, and then talk about really why Caltrans and why I'm personally interested in CFD, and then give you some examples of applications. Again, not so much intended to get into the nitty-gritty and details and insights of that, except to give you some more, just more examples of how we're using it, and then to talk about some other applications that we're looking forward to in the future. So to begin with, what is CFD? You know, not to bore you, but this is kind of one definition that's a little more on the technical side. It's the applied mathematics, physics, and computational software to visualize how liquid flows and affects objects as it flows past based on the Navier-Stokes equations, which describe how velocity, pressure, temperature, density of a moving fluid are related. A little boring, a little technical. Here's mine. I define CFD as really cool code that can simultaneously frustrate, enthrall, mesmerize, and bring a grown engineer to tears as you labor in love and hate in an attempt to understand more, only to realize that finding that elusive answer is much harder than you originally thought. So my experience with CFD kind of started back in graduate school with Flow 3D. Again, I didn't spend a lot of time there, but I started off with some commercial code, got interested in it, and I think that kind of planted a seed in me. Later on, through Argonne, and I was trained a little bit in Star CCM Plus. Again, dabbled around in it, not too seriously, but enough to kind of get some insights on how Star CCM Plus works. I've probably spent the most time with OpenFOAM, which is an open source software package. It's grown a lot in popularity, and it's one of those that'll bring you to tears, but it's very powerful in its own right. And now most recently, VFS Geophysics, which is kind of some academic code that's partially open source, partially not. Kind of started with the University of Minnesota, and now it's kind of been, the main developers are now over at Stony Brook in New York. So what's the difference between all these codes? You know, are they all pretty much the same? Those are my dogs. I'm very proud of those dogs. So, you know, all these different codes, they're kind of intended to do the same things. Aren't they all more or less the same? Well, what I found is they are all dogs, but they're more like this. You know, they do have, you know, 2 ears and a tongue and a wet nose and a tail, but they act and function very differently, you know. But they're all dogs, but just have their own unique features to them. So the next question really is why CFD? And I give three reasons. First, I can't kind of get away from the beauty of physics and just the technical side of it. I think it's just fascinating that we can compute some of the things that actually happen in nature to such high precision now. Secondly is just the power. You know, it makes me feel powerful, you know, because, and I think we should use CFD just partly because we can now, and we should do it. And the table here is, and again, these numbers aren't really meant to be hard and fast, but just to give you an idea that moving from normal depth and 1D calculations on down to 2D and 3D, I like the last column. Again, these are just rough, but from my experience, you know, normal depth, 1D calculations takes a computer like 1 second to give you an answer typically. You know, 2D model, I know some people are better than me, but it usually takes several hours to get a simulation to, especially an unsteady simulation to result. So it takes roughly the computer about 10,000 times more effort is the way I see it. 3D, you got to run on multiple cores, maybe 200 cores sometimes, you know, and you got to run it for days. That's about 10,000 times more effort than the 2D model, or 100 million times more than a 1D model. Again, don't hold me to those numbers, but that just gives you a range of a feeling of power in CFD. And I tried to come up into terms of what does that really mean? Well, you know, we came up with this idea of horsepower at one point. What is horsepower? Well, horsepower was really related to what a horse can move, and so we can compare engines and things to what a horse can do. Well, I'd like to think of it in terms of engineer power. I know there's teraflops and things like this that describe the power of computing, but I like to think, well, what can an engineer do, and compare that to what a computer can do. Well, using the same table from before, I look at it this way, if I'm good and I really worked hard at doing step backwater calculations, maybe I could do a simple HEC-RAS calculation in a few hours if I had to do it on my own. Well, in that light, it's one CFD simulation. If I worked at it 40 hours a week, for 40 years, or for all year long, it would take me basically 100,000 engineer years. So this again makes me feel much better about CFD, because even though people think it takes 5 days to get an answer, I look at 100,000 years and I think I'm getting a bargain, So, and the last reason is curiosity. I lay awake wondering about things, and usually CFD sometimes comes to my mind as maybe a way I can find the answer, but as I described in my definition, most of the times it still eludes me, but that curiosity drives me forward. Okay, moving on to my most recent endeavor, which is working with VFS Geophysics. Caltrans has entered into a one-year contract with the university and with Dr. Ali Kroshanajad, who is one of the main developers of the program. And you'll see some of his work. I give him credit now for what I'm going to show you in a minute. The intent of this was first for him to analyze one bridge that we all know very well in Caltrans, and some of you know the Feather River, to see if he could simulate the scour that was going on at this bridge, which has been well documented. And the project itself was more justified financially on the basis that we had a failure of the Tex Wash bridge, which I think I presented last time, which was basically a desert flash flood. And the HEC 18 equations and things like that aren't really designed for that. So that was kind of the justification. Let's use some advanced modeling, see if we can learn something to address these kinds of problems. Also with this contract, though, and one of my personal reasons was that was the kind of the condition that was put out there for us as in Caltrans to be able to use this code in the future. So we're not just paying for him to analyze two bridges, but for him to provide training, support, collaboration, and allow us to do our own simulations on into the future. So, and also to use their supercomputing cluster as well. So I think we're getting a good deal with this. What was attractive about VFS Geophysics? Well, again, they've spent a lot of time working on the sediment transport piece. Open foam, those types of codes are very general, and there are people that are developing pieces to do scour, but it's not, I don't think, quite up to that same level of effort or refinement that VFS Geophysics has. They had used it prior with the Minnesota DOT on the Mississippi River. They modeled a massive stretch of river using LES, which is a very advanced form of turbulence modeling, and seemed to model the scour. So I was very impressed with what they had done. Most the software can run in different turbulence modes. It can do free surface modeling as well. And the last one here, the immersed boundary method, which I wasn't very familiar with, but it was very attractive. It's the idea that instead of developing a mesh that's really refined around all your objects, you create basically a structured mesh, a curvilinear structured mesh, and then you can just stick objects into that mesh, and then the code itself will define where those boundaries are, which at least had the appeal of being maybe a much simpler way to deal with the meshing, as well as maybe a way of solving some of the sediment transport issues as well. So those were some of the main reasons for it. So let's look at the first example again. What's Dr. Kroshanajad has done with the Feather River. So this was a site at which case we had, if you look in the chart on the right, we measured about 30 feet of scour during this event that was going on. And so we wanted to see how his code would work. It's already been studied once at Turner Fairbanks in their flume. I think Turner Fairbanks used Star CCM Plus as well to model it, not I think the hydrodynamics, but maybe they've done Scour, I think, since. And I've worked on it with open foam, just the hydrodynamics piece to it. So it's been looked at. Let's see what the VFS geophysics could do. And in their case, from the red line down was their main study reach, which was 600 meters long. Again, it wasn't the full 100-year flood, which would have gone way out into the floodplain. It was really this event that occurred in March 2011. And like all academics, they want to publish papers. So it turned into be more of an exercise than just give us the Scour number that you get. They wanted to compare different things, study different things, and see what we could learn. So one of them was our inlet condition. And in this picture, again, this red line here, they first tried this, let's just feed a uniform flow in at this red line and kind of ignore what's going on upstream. Second case was they said, let's develop the flow around this red line by kind of simulating the flow just in this region and get it so it's kind of well-defined, and then let it introduce into here. And then in the third case, they said, no, let's look at this whole upstream bend. So they basically went from this dashed line to the red line until this was well resolved. Then they took the output of this and fed that in as the inlet here. So you try the different conditions. Does it make a difference? Well, we'll see in a minute. Comparing the different turbulence models, as well as comparing what we call a rigid lid, or basically it's like a frictionless solid lid on the top where you're not really modeling the air, versus the free surface modeling, so you are modeling the air. Okay, so here's some of the results, both the URANs, which is more of a, you can see is a time averaged result, versus what you're seeing in LES over here is you see all the instantaneous and smaller vortices being generated. So here, so you can see the similarities, you can see the differences. Did that make a difference in terms of the Scour result? And again, here's the three inlet conditions. It's a little hard to see, but certainly in this, where we modeled the upstream river, you can see more vortices and things coming downstream into the flow. Does that make a difference when it gets to the bridge? So that was one question. We'll see in a moment. So this is the flow through this region using that upstream inlet condition with the bend in it. So you can see it's pretty well resolved. And here's what came out of the vorticity looking at this. So let me play that one more time. Oops, back up here. Oh, well, I can pass that. It's okay. And here's basically the water surface. What turned out with the water surface, because the flow depth was, I think, close to like 40 feet deep, right around the pier, maybe you have a 2-foot drop from one side to the other side. Not a great difference, so it didn't have a huge impact on the flow. What it does have a huge impact on is the time of the simulation. It requires maybe, I'm going to say 20 to 30 times longer to simulate things when you are simulating the free surface like this. So kind of quickly, because there wasn't a huge difference in water surface, that was kind of abandoned for the rest of the project. But it was just kind of shown that it didn't really matter too much. And here's the bed scour evolution. You can see the dunes moving downstream and starting even upstream. Scour underneath this is the bridge pier that had the large amount of scour. This is a little bit deceptive in the sense that you see the sediment moving underneath the pier, and that really happened because the pier was completely undermined, and it was well, there was piles underneath it, but basically the flow was going underneath it. In order to really get this proper simulation, this footing had to be lifted up like 1 meter to allow flow to go through there. Without the flow passing through there was kind of a stagnation zone out in front that was really not allowing the scour properly to happen. So this is one of the lessons learned was that there are still some weaknesses in their immersed boundary method that are not unsurmountable, but right now they're in the code. It's a limitation. Again, here's Similar thing with an oblique view of the scour that's forming underneath this foundation here. The results showed basically two things. It's a little hard to see because of the size here. This was what was measured. A little hard to see, but these are the LES and URANS runs. Bottom line was that the scour depth was similar, but the spatial distribution was different. It was not, didn't really fully capture that. So there's still issues, but it's a step in that right direction. I think I've highlighted most of these things. So basically the other thing was that did that upstream inlet matter? And bottom line was that the time the turbulence reached the pier, it made very little difference on the scour itself. At least they weren't able to capture that. I think I've mentioned most of these other things. Our next job is to go through the desert wash. This is Tex Wash bridge failure. It's been studied again by myself a little bit, as well as Berkeley's looked at it. I'm going to skip over that one. So again, that's the future work. What I've done with the code since then is look at the American River. American River has 4 bridges in it, and the most downstream bridge is one of interest, which is the one here, the larger of the piers. The reason they're interesting to me was that their shape. First off, the pier widths are not constant. Secondly, this strange foundation or pile cap that's stepped, and so it came down to, well, this is a scour critical bridge. There was a proposal to put rock. The rock should be based on HEC 23, based on the A, which is like the pier width, and it should extend 2 times. So the question was, well, should we use this distance? Should we use this distance, this distance, this distance? What would be the right A value to use for this case? I thought maybe CFD might be a good way to look at the shear stress and maybe decide that. In this case, we set up a rigid lid model this time and ran LES, 80 million nodes, and simulated basically 100,000 engineer calculation years. So that's, I didn't really keep track, but I'm using that as my basis there. I'll show you a quick turbulence here. So you can see these downstream spots. These are basically the railroad bridges that were upstream, sorry. And they were generating some turbulence, as you can see in this image. But by the time that they reached here, not so much so. Even these upstream pier walls that were right in front of the one of interest were not showing much. But this was based on one frequency of vorticity, maybe a shorter, like a half hertz might have shown some more. This was our shear stress distribution. Again, looks like maybe there was some protection from this upstream pier because the blue is less shear stress. Of course, there's a little blue around each of these because there's some limitations on again, these bluff bodies and how well the shear stress is predicted right there. It didn't really answer my question. Ultimately, the environmentalist said you can't put rock, so it didn't really matter. But it was a good test case anyway, just to see can we model this. Quickly, another case was debris loading. This case is a 3-phase flow where I modeled the water, the air, and the sediment transport, looking at the shear stress underneath the debris, comparing that shear stress with the shear stress on the left, which is with no debris. You can see obviously much higher shear stresses. And then looking at a scour difference, significantly more scour occurring with the debris than without the debris. I'm not saying that's at equilibrium, but that was a point I had to stop before to get this presentation together. Other future projects, scour in a skewed pier, a low flow. I've always wondered about this. When you see a low flow that's skewed to like a pier wall, people say, well, in a high flow, it's going to be straight. Well, it's true from the surface and maybe even the depth average value, but I always wondered, is there still a skewed flow down at the bed, which is where you really care about. So I think CFD could answer this question. That's the one thing I want to look at. Again, some more complex shapes, like this shape for the Fern Bridge in Eel River, where you have a strange-looking foundation, a pointy foundation, plus a strange-looking pier wall. Again, I don't think HEC 18 can deal with these kinds of problems very well, so CFD is good. Lastly, forces on bridges and countermeasure designs. So About out of time, so I would just kind of conclude by saying, so far my personal opinion is I find CFD very challenging, but I like challenges. I think it's really important we have calibration data, and it seems to me in general that the hydrodynamics aspect of CFD is a little stronger than the Scour right now. Scour needs some more work. And my parting thought is that we're not there. And I realized when I said that, I go, why did I say we're not there? But yet I see how deeply CFD is embedded in me now. I take it very personal, I think. But the Scour still needs work. But in the words of Martin Luther King, we must accept finite disappointment, but never lose infinite hope. So I'm very hopeful that the CFD will eventually be the standard, maybe 10 years down the road or 15 or 20 years, but I like to be out there at the front if I can. So anyway, with that, I'll entertain any questions you might have.
Kevin, we've been wondering about just the computing power we would have to have access to serious CFD modeling. So for these kinds of applications. So for the examples you showed us, was the clustered supercomputer always necessary, like a non-negotiable requirement?
For the size and type of analysis, yes, I would say so. I know that Young Lai's working on some code. I can't speak for him. Maybe he's. I think if you want to simplify things down, then I think you can get to less CPUs. But I don't know to what point. At this point, it seems like supercomputers are pretty necessary. But, yeah.
We have time for one more question.
Oh, one in the back.
Have you done any comparisons to simpler methods, like doing a 1D or 2D scour analysis, looking how it compared to the 3D output?
That will be one thing we'll do at Tex Wash. As far as running a model to develop Scour versus getting the inputs out of it and plugging it into equations, yeah, we've done some of this. But again, the Scour part is still kind of a novelty for me and for, I think, the industry as a whole, in terms of getting some hard Scour values out. So I can't say too much about that. Oh, yeah.
For the Feather River, the Pier Scour generating kit, that pier has 90 hives.
It's true.
Similar to that?
They were not. They were not in it. That's, again, a limitation, partly due to the resolution you would need, but also to, I guess, just the way it deals with the immersed boundaries. I think we could have done it in a kind of coarse form of a pile, but not the flanges and things. Okay, I think I'm out of time, so thank you for your attention.